with work experience in infrared photonics and nonlinear optics. He's a researcher in the behavior and fidelity of quantum networks, which involves designing experiments, as you're going to see today, and simulating EPR entangled states, primarily focusing on how quantum networks display inherently chaotic behavior as the networks are increased in size and scaled from within a lab to a wider network across existing classical network infrastructure, such as in optical fibers or free space communication. John is also investigating how established principles of network synchronization among nodes and signal repeater systems can be extended to quantum information theory in general, and how disorder and noise affects recoverability of quantum information from transmitter to receiver. I'm loving this already, the mention of noise, how it's part of this contingency is part of the system. Okay, over to you, John.
Oh, thank you. I wonder if I could get the screen lifted up, if that's a problem, or just I want to try and use the blackboard as much as I can. I don't know if it's controllable.
This one, I'm not really sure what will happen if we just.
I think does that move? Sorry for. Oh, it's already.
There's already there.
Yeah.
Okay.
Yeah, a little bit more. Just a little bit of maths, because the maths is actually quite interesting once you get to look at it. Also, today I was actually having an interesting journey around Dublin because I was called in for jury service, and they let me go at 10 o'clock in the morning after coming in at 9, so I have to wander around Dublin for a bit, you know, like a quantum particle of sorts. But I picked up this little book for €6, which actually doesn't have much about quantum in it, apart from a quote by Stephen Hawking, but it's mostly about fractals, which are kind of like the dioramas of chaos. But it turns out that there is actually quite a bit of overlap. So my talk, I can write it up because they gave me colored chalk. It's almost like the picture of the hand actually that Nadia showed on her slide. It's building bridges, trying to build between basically so-called pure quantum systems. Bridges are, you know, kind of almost like a wormhole of sorts. And if we could call them, if we like, quote unquote, classical systems. And really, much like the wormhole here, the thing that links them together quite a bit, in my understanding, is this concept of networks, and specifically nonlinear networks. And the reason why I've been convinced by this is because there was a great physicist and mathematician who lived, and still alive actually, in the did most of his work in the 1970s, called Kuramoto. And he basically developed a theory of oscillators, and how oscillators can display sort of this principle of emergent synchronization. Now, it turns out that synchronization is a classical phenomenon, classical in inverted commas, so we could put it over in this category. We like sync. And what does it correspond to in quantum systems? Well, it corresponds to the phenomenon that you mentioned, actually, that's kind of at the core of quantum communication as we're understanding it now, which is entanglement. In a way, we could actually start to draw a bridge between these two, as I will hope to convince you, trying to preach it like a street preacher at this point. If we think of them in terms of Kuramoto oscillators, that's to say, thinking more and more that every network that exists in the world, you know, complex, nonlinear, and so on, dynamic, can be treated as a system of Kuramoto oscillators. So what are Kuramoto oscillators? Well, this is where the maths kind of comes in. If we want to think about a system in terms of its evolution, you can think about it in terms of Cartesian space. You're probably familiar with Cartesian space from school. So we have like X, Y, Z coordinates. They have nice little maps that we can draw here, maybe X, Y, Z. They're useful for, again, classical systems. But for quantum systems, sometimes you want to use a different type of coordinate system. And it turns out the coordinate system, which is very useful for quantum mechanics, is this concept called phase space. Phase space is an imaginary or complex way to represent dynamics. So for instance, we could have kind of like a diagram like this, and instead of having X, Y, Z, we could have I, which is literally imaginary units, and maybe time. It's evolving in time, or in maybe even imaginary time, which was an idea proposed by people like Stephen Hawking and others to describe, for instance, the Big Bang. But what does phase space look like for Kuramoto oscillators? So if we have a network of Kuramoto oscillators, and there may be different oscillators, maybe yellow for one node, maybe the white chunk here for another node. They're separate, they might be governed by separate variables, separate dynamics, but they're nevertheless linked together to some degree. And maybe one could be the source node, maybe one could be a client, and maybe one could be a memory. And you'll notice source, client, memory has nothing to do with it being quantum or classical. It's a bridge. There are, in fact, of course, quantum source nodes, entanglement nodes, quantum memory nodes, experimental for sure, but they exist in some cases, and of course, clients. There are people that are maybe using it for quantum key distribution and so on. So the idea is, could we actually model this in some way which bridges quantum systems and classical systems? And indeed we can, if we treat the nodes as oscillators in phase space. So in the circle, we could have them maybe in a dynamic where they're just basically unsynchronized, maybe in different positions in phase space, like this, where source, client, and memory are maybe, if you like, in a state of unsynchronization, represented by this, and maybe evolving over time to a period of synchronization, like this. So represented messily for sure, but in this case, actually overlapping each other in this representation here. But that turns out to be, okay, maybe a little bit cumbersome, but a kind of a natural way in which you can understand state evolution. This is evolving over time, but in the phase space, or sometimes called complex plane. Now, what does this have to do with networks? Well, the idea of networks is if they're evolving, they're reaching some type of synchronization. Maybe there's a way in which one could actually push this into synchronization, maybe to bring about better communication, maybe better understanding of systems dynamics and so on. And this is where Kuramoto came into the picture. He developed a very, very beautiful formula in which you can actually model entire state evolution by putting, if you know the phase information for each of these nodes, and phase is sometimes given this symbol here, over time, is equal to the frequency, the natural frequency of the system, plus the number of nodes in the system with the sign of the phase, let's say, of this node, let's call it 1, minus the other node, the phase of the other nodes 2, and minus the phase of the other node 3. And so these, of course, n in this case, that would be 3. So these equations can actually be used very, very elegantly, very, very easily programmed on a computer, say, or on a network of oscillators. And what it turns out is a lot of nonlinear dynamics sort of emerge from these formulas, and they're called Kuramoto oscillators. Another attractive thing about them is that they can be actually modeled using graphs. So this actually allows us to use a whole branch of mathematics called graph theory, which has tons of attractive, if you like, figures of merit, vectors, indices even, that are very, very well understood from the point of view of classical systems to do with synchronization. So the actual idea then sort of has been explored, not enough in my view, but in the design of quantum systems, we're often talking about, okay, we have to build special systems, maybe low temperature superconductor systems, maybe nonlinear optical systems, such as I've been working on a minute. They're very cumbersome, they're very complicated, they are very heroic experiments, but they have problems of scale. You know, they cannot be scaled up to large scale, at least not cheaply. So wouldn't it be nice if we could take systems that we already know quite a bit about from graph theory, from classical systems, Kuramoto oscillators, and in a sense, if you like, make, you know, I cannot believe it's not quantum equivalence, you know, like the brand of whatever it was, butter from the US called I cannot believe it's not butter. Fools people into thinking it's really butter, but it's not butter. It's a bit like that, which I'm trying to demonstrate here. So these are a series of 24 oscillators, oscillating LEDs. They're almost like metronomes in a sense, and in fact, people have made literally Kuramoto oscillator networks with metronomes that they use to tune pianos, and they've showed very, very spookily the behavior of non-locality, which is actually a core feature of, you know, what was considered to be the pure quote-unquote quantum systems. But Kuramoto oscillators of this sort are everywhere. They're in swarms of insects, there are neurons in the brain, and for a long time, in fact, even people like Roger Penrose have puzzled, like, why does the brain actually display principles of non-locality? Why is this principle of self-organization so quantum-like in its behavior? One of the reasons may be, in fact, there's a lot of overlap already in terms of mathematics between phase space dynamics and systems of phase oscillators anyway. So that inspired me to design this system, which I called Feynman's Fireflies, after the physicist Richard Feynman, because it actually turns out if you delve even a little bit deeper into the mathematics here, you can kind of get things like path integrals based on the phase space dynamics. I won't go into it in much detail, but it turns out that there's a principle called action, and action turns out to be related to a thing called the Lagrangian, which is the kinetic energy minus the potential energy. Turns out that synchronized networks can actually be represented by path integrals, believe it or not. But that's kind of a long way of saying that, you know, we could just always build the damn thing, and I did, to show how it works. So this is a series of 24 oscillating LEDs with photodiodes, and by plugging it in, the only way it's connected is through the power and through the light that each of the LEDs shares. You can see kind of almost like lobes forming between two of the sections of LEDs. And if I hide it in shadow for a while, down here, it'll start to display, very interestingly, these things called fractals. And the fractals are sort of like at the edge of order and disorder. And what's interesting about them, and it kind of comes to the point of scale-free networks, is that fractals are scale-free. If you have a fractal made up of 5 LEDs, kind of looks the same and even behaves the same way to a certain degree as a fractal made up of maybe 100 LEDs or 100 nodes, if we want to use the parallel solve of networks. So I can actually see here, it's a bit like a magic trick. It's kind of displayed. You can see the green LEDs shining a little bit through it. But if it's left in a kind of a semi-lit or dark room, it actually has these sort of almost like spiral-like forms, which you do see actually in, very spookily so, in things like signaling neurons, fireflies, even squid, even the way in which animals flock has this sort of weird, almost non-local like behavior. There's a very good story, for instance, of David Attenborough. He went into a cave filled with bats. And what puzzled him most of all is that this cave is so complex, the bats can't see. They're using their sonar, but in order to navigate the cave with all the bats flying around, they would have to have huge computational power. I mean, a bat's brain is the size of a pea. It's powerful for sure, but how does it compensate for all of the nonlinear dynamics? The reason is that there could actually be a lot of principles of emergence here going on, both with classical systems, synchronization, and quantum systems as well. So this is all my way of saying that I think people, although they're attracted to studying quantum systems, like I am, in terms of optics, nonlinear optics, more and more, I think we have to push into this more general study of networks and network dynamics, and particularly with regards to Kuramoto oscillators. And that's kind of the long and the short of what I wanted to talk about. It was more of a kind of show and tell rather than a tell, but it's also to share, in a way, kind of to spread the good word that if you want to study quantum physics, a lot has been done with this already. The history is very rich. Started with Schrödinger, Heisenberg, Dirac, Feynman, and so on. Continues to this day for sure, but a lot has still to be done with bridging it with classical systems. And that's where I think a lot of the interest in the field is actually going at the moment, because people think when they want to study quantum physics, okay, they have to read all the material. They do, but if they want to do groundbreaking research, they may actually have to rediscover, in a sense, some of the principles of network theory, of network synchronization that is very rich and may not be as intimidating, from the first principle. Because one thing in which I wish I had done was focus more on the classical systems first, then jump into the quantum systems later. So that kind of brings me to the end. I think if anyone has any questions about anything I talked about, be it the maths, how I built this thing, did I use glue, or did I use did I pay someone to do it? Yeah.
Can I just ask about the photocells? Is there some kind of feedback aspect to it?
Yeah. Yes. Yeah.
So we'll take questions at the end.
Okay.
Sorry. Mm-hmm. Yeah. So that's a good question. Now there is feedback to it, and a threshold as well, which is important. Yeah. Mm-hmm. Okay. So I think that probably is it for me. So okay.
Yeah, thanks so much, Joel, for this fascinating presentation. And I find it fascinating that you don't really have to go to IBM to work with those expensive chandeliers, with those trapped iron technologies, but you can construct a system of phase oscillators and also experience this simulation of quantum systems yourself, which is brilliant. Okay.
I can answer your question. So the tension between treating pure quantum systems as entangled oscillators versus synchronized oscillators, it's a matter of scale. So for, let's say, if you have two nodes in a quantum network, maybe a source node as well, and it's sending entangled pairs, like a polarization or phase entangled pairs to Alice or Bob. There you can treat perfectly well, kind of standard use entanglement. It's when you actually extend them to networks and make them scale-free networks, much like the internet, then you run into kind of problems. Because much like in classical physics, you do encounter similar issues of almost like multi-body dynamics. The quantum dynamics do get more difficult to model, to simulate at scale. So therefore, there could be other models that exist in the classical world of network theory, like Kuramoto dynamics and so on. There you get into kind of the issues of synchronization, where it may not be useful anymore to talk about the system being entangled, rather the system being synchronized or having emergent synchronization. And in both cases, you can use phase characteristics, phase space formulae. For instance, in quantum systems, it is using sort of translation from Fourier analysis from something maybe in frequency space, to phase momentum space, something like that. But in the network models, phase space dynamics is kind of how they're governed anyway. So it seems like a kind of a natural enough translation for it to be almost like borrowed at that point. But there is a tension for sure between the two. It's a matter of scale. So it's still better to use, let's say, pure quantum dynamics or let's say simple networks. But when they start to grow, it kind of becomes redundant at that point. At least we're still talking about actually building them as well and trying to do some type of forecasting, let's say, with graph theory or something like that.
So when you're building the bridge, one of the things that is involved is scale.
Yes, exactly. Yeah, it's scale, because the thing is, as the networks get more complicated, as more clients are added to them, and as I'm not 100% familiar with the whole concept of quantum stack insofar as how you model it mathematically, but I'd imagine you have to model using some type of graph theory. And at that stage, once it starts simple from source to from architecture, then to clients, then to network, and then to maybe infrastructure, something like that. I'd imagine the networks get more complex. So in order to do forecasting or to predict or to apprehend emergent dynamics, I'd imagine you'd have to use some type of graph theory, maybe borrowing from Kuramoto oscillator dynamics. There is a tension, it's not that there. I mean, it's not real, for one thing. Like they're almost like, in the sense that Newton, when he was developing, kind of classical mechanics, what you call it classical mechanics, people like Leibniz and so on, they did correspond and say, look, what you're talking about here is not actually real. It's kind of like borrowing on mysticism almost, because like it's not as if the planets or the things of the sun have a big like letter M with M1 or M2 written on it. It's totally abstract, It's not really naturalism, if you want to call it that. But that's been a problem from physics from day one. I mean, if you want to look back in time, back in Aristotle's time, there was like concepts like sympathies and antipathies that, like, if you want to understand how a leaf falls, you say, oh no, it's tracked to the ground and so on. You just videotape it or look at it. It's literally, yeah. But then, of course, people like Galileo came along and they came up with these crazy concepts like, no, you have to drain all the air out of the world and have a feather falling at the same thing as a leaf or a bowling ball. That's mad from their point of view. It's much like that with network science as well. You have to kind of suspend belief and say that we actually don't know how to really model a network. In reality, we have to make up a fake, kind of crappy model that just hope it does the best, Maybe with AI it's different, because AI is actually a game changer in the sense that it does really look at the whole picture and is able to process it. But that's not doing physics, in the sense, let's say the Newtonian Cartesian sense of doing physics,
But in a sense, quantum physics is like breaking a little bit of this, because you start thinking of the scale, start thinking of what is actually going on in the smallest possible scale.
Yeah.
So
that's where chaos theory comes into it in a big way, because chaos is actually how the universe works in the natural sense.
But in the sense of, chaos comes into the picture when we talk about scale.
It does, yeah, absolutely, because it has to work that way. Because the universe, it naturally, we assume it's efficient, that it's not, it's not like the kind of, beautiful mind picture where the universe has like, God scribbling on the blackboard, where it is actually some type of very simple emergent features that make things work.